Good afternoon everyone, and welcome back to this session on copulars. According to YouTube Studio, I have an excellent connection, so let's hope that continues. And we're going to kind of pick up where we left off from. So I'm going to assume that everybody that's watching this has seen the first video, but I'll assume that you saw the first video a few days ago, so a brief recap will be helpful. So let's just get the presentation up. And just to talk about, hold on a sec. And just to recap what we're trying to do with this presentation overall, with this discussion overall, is not to go into all the details on all of the technical stuff around copulars. So, as I said, things like Sklar's theorem, the axioms of concordance, all that, they're important, but they don't really help you understand intuitively what a copular is trying to do. And that's really what I'm hoping to do now, is to talk about, help people understand intuitively how copulars work and how you can think of them. So there will be some examples, because I think doing this stuff with numbers can make it a little bit more real rather than just thinking in terms of pictures, but it is going to be based on the intuitive and the practical side rather than the theoretical side, which is still very important, but it's not what we're going to be talking about today. So first, let's recap on univariate continuous distributions. If you recall, these are some normal distributions, and these are density functions. So when you're looking at a density function and you put in a number, you're essentially saying that the area under the curve up until that point of the number, that is the probability that some random variable is going to be less than that number. So here the probability that x is going to be less than x2. And the area under any normal density curve, or any density curve, is always going to be equal to 1. So describe it as the probability that x is less than or equal to x2, the probability that some random observation x is less than or equal to x2. You can also talk about it mathematically and say it's equal to the integral from minus infinity up to x2 of the density function. And you can define that as capital F of x2, which is the distribution function. Or you can just take the distribution function itself and read straight off that. So in that case, here's a distribution function, and instead of looking at any areas, you just read up from the horizontal axis here up to a particular point, read across, and that tells you what your probability is, your probability of some random number being less than or equal to this number here. And as such, the probability distribution function always goes from 0 up to 1. Impossible to certain. So, got through that in about 3 minutes, which is quite a bit quicker than we did last time. If you do need more information, more examples on that, just refer back to the first presentation that I did. And there, to make my moving on the mouse redundant, here's the example with x2 and just reading off f of x2. So, the feature of the distribution function. The input can be anything, subject to the limits of the distribution. So if it's normal, what you put into it can go from minus infinity to plus infinity. Log normal from 0 to plus infinity, and so on. And this is important. Bear this in mind when we come to talk about copulars later, because they are different. But the output is always constrained between 0, impossible, and 1, certain. So capital F of x always lies between 0 and 1. So a recap on bivariate continuous distributions. If you think about the density function for a univariate distribution as being a curve and the area under the curve is 1, a bivariate density function, you've got a three-dimensional shape, you've got a cone, and the volume under that cone is equal to 1. So here, you're not looking at the probability that one variable is less than x or one variable is less than y. You're looking at the probability that some random variable x is less than x1 and some random variable y is less than y1. And instead of looking at an area, you're looking at the volume under the curve. So you're essentially taking, if you think of it as being like a cake, you're taking a slice of cake, the volume of the whole of this dome here is 1, so this volume here is your probability. And you can see that this is going to be affected by your correlation coefficient, how well correlated these two series are. If they're strongly positively correlated, you've got a much greater volume than if they're negatively correlated. So that's how a bivariate density function works. And again, you can see these go, we curtail them here to -3 to +3, but these can go to any limit at all. So, as I said, we think about this in terms of volume rather than area. The probability that x is less than x1 and y is less than y1, or in a more wordy form, the probability that some pair of random observations, x and y, is less than or equal to x1 and y1 respectively. Again, you can mathsify this and say it's equal to the integral from -infinity to y1 and -infinity to x1 of f of xy dx dy. So you just do a double integral. And that then becomes your bivariate distribution function, capital F of x1, y1. And again, you can just map this function. So you can read off here where x1 and y1 would be on this surface, read across, and then read to the vertical axis, and that tells you what your joint probability is. And again, you can see that if you'd read off from x1 and y1 to here, your joint probability, when you read it off here, would be much lower. So again, features of the distribution function. The input can still be anything, subject to the limits of the bivariate distribution. So if you've got a bivariate normal distribution, your inputs can be anything from minus to plus infinity. Log normal can be anything from 0 to plus infinity. So your normal distribution, as I said before, if you said people's heights were normally distributed, in theory you could look at the probability that someone was 20 feet tall or minus 5 feet tall, and the normal distribution would still give you a valid answer. So the inputs are not constrained, but the output is still always between 0, impossible, and 1, certain. F of xy is always between 0 and 1. That is what is always the case for a distribution function, because it's telling you a probability. So we start on this last time, deconstructing a bivariate continuous distribution. And the bivariate normal distribution is a nice easy one to start with because it's got a fairly limited number of parameters and it's pretty well behaved. So let's think about it in terms of linking the distributions of x and y. It's defined by 5 separate parameters: the means and standard deviations of x, the mean and standard deviation of y, and the correlation between them. And that's all you need to give you a joint distribution, f of xy. But as I said last time, some of these describe a univariate distribution. So the mean of x and the standard deviation of x, they tell you about the characteristics of the marginal distribution of x. And mu of y and sigma y tell you about the marginal distribution of y. So when you're thinking about a bivariate distribution, you could think about it as being 2 univariate normal distributions and something which links them. And if you wanted to generalize, then you could think about the thing that links them as being a copula. It's a copula which joins them. But you need to be careful about how it joins them so that you can do it in as general a way as possible. Now, I'm not sure whether I covered this last time, but it is just worth covering it again, talking about it again, because it is important. Because copulas are quite cool, they're quite neat, cool for actuaries. It's nice to be able to use these more complex mathematical techniques, but if you're doing any sort of financial modelling, the approach really should be you use the simplest thing possible that can give you accurate enough results. So whilst copulas are great fun, you shouldn't necessarily go to a copula if something more simple, like a multivariate normal distribution, couldn't do the job properly. So why might you bother using a copula? Well, in broad terms, it's because the data set you're using can't be adequately fitted to a standard bivariate or multivariate distribution. And there's a number of reasons why this might be. It could be that the marginal distributions are different from each other. So you might have one data set being normally distributed, another having a t-distribution. Or you might have both t-distributions but with different degrees of freedom. Or it might be that you've got, say, normal distributions for your marginal data, but whatever links them in the middle is not normal. It's got very significant jointly fat tails. So you need to model your marginal distributions using one approach and the thing that joins them using another. But you only do this if a more standard approach, a multivariate approach wouldn't work as well. And the reason for this isn't because you get the wrong answer. This is more a sort of a philosophical question. The way that I think about it is that the more complicated a model gets, the more faith people often have in the model. So if you use a very complex modelling approach, there's a risk that people will think it is going to give you better and more accurate predictions than using a simpler approach. And that might be true, but it's not necessarily an order of magnitude difference. So there is merit in using a simpler approach if it means that people will treat the results with an adequate degree of respect and won't think that it is some astrological prediction of the future, and recognise that it is just a statistical projection, statistical estimate. So if your standard distributions can't do it, then copulars can give a very solid alternative. So anyway, back to copulars. As I said before, you have your two marginal distributions and there's something that's joining them, which is a copula. So what is this something which is joining them? Well, let's look at what it's not. A bivariate distribution, as we've seen, has the form f of xy. So that's the probability that some random variables x and y are less than a given small x and small y. And the inputs aren't constrained except by the distribution. And it gives an output between 0 and 1, which is a probability. Now, a copular distribution function also has an output that is between 0 and 1. But you've got to standardise the input somehow, because as we said when we were looking at the reason for using a copula, it's so you can use a whole different range of marginal distribution functions. But if you're using different marginal distribution functions, you need to make sure that when you're putting them into the copula, you're putting them in a way which means they're consistent somehow. So if you're using a gamma distribution or a t distribution or whatever continuous distribution, whatever output from those goes into the copula is the same for each of them. So one way of thinking about this is if you had these different marginal distributions and you stretch them and reshape them somehow. So you imagine that it wasn't necessarily a normal distribution, but was instead a t distribution. So you'd be kind of squashing it down a bit in the middle and raising the tails. Or it was a gamma distribution. So you'd be taking all of your observations from the left-hand side and pushing them and squeezing them up so that everything became positive. Now you can do that to any of the distributions, but the important thing is that you have the order of the observations staying the same. So if you thought of this as being a time series between two sets of equity returns, that if they were normally distributed and your lowest return in one period happened at the same time as your fifth lowest return in the other period, even if you squashed and stretched the distributions, you still have that link between the lowest in one and the fifth lowest in the other. So what this means is that when you're looking at a copula, it's drawing the marginal distributions based on the order of the observations in those distributions and not the value of those distributions. So how do you do this? What's the easiest way to do it? And the easiest way to do this is to change all of your marginal distributions, whatever they are, into the same thing and make these the input for the copula. And the best option for doing this, and the option which is used when you're building a copula, is a uniform distribution, and a very particular uniform distribution, which is the cumulative distribution function. So what this means is that for each marginal distribution, when we look at the observations, we convert those from what you see to the cumulative distribution, and we plug that into the copula. So if, say, we had a return of minus 10%, and that was sitting at about 0.15. So if you calculated capital F of x for minus 10%, it came as 0.15. The 0.15 would be your input into the copula. So what you've got here is, instead of f of xy, your cumulative distribution function based on the observation x and the observation y, you calculate the cumulative distribution function for x, the cumulative distribution function for y, you input those into the copula function, and this gives you the joint probability that f of x and f of y are less than f of capital X and f of capital Y. So a copula joins essentially two probabilities to give you a joint probability distribution. So C f of x, f of y is the copula distribution function. The inputs are the cumulative distribution functions for x and y, and the output is the probability that the cumulative distribution functions of those two random variables is less than f of x, f of y, respectively. So it's independent of the shape of the distributions, because when you have your distribution, once you've calculated f of x, f of y, the results, what you're going to be chucking into your copula distribution function, they are going to always lie between 0 and 1. So that's how the bivariate normal distribution, for example, and the bivariate normal copula are different. If you look here, we can see these two charts we've already seen. The bivariate normal distribution, where you've got this cone, the area under it is 1, and these axes here actually go off to infinity. And if you integrate from minus infinity upwards, then you get this surface, which is the cumulative distribution function, where your inputs are still going off from minus infinity to plus infinity, but it is very definitely going from 0 up to 1 on the vertical axis because it's a probability. Now, for the bivariate normal copula, the distribution functions, the inputs run from 0 to 1 rather than any other range. And what that essentially means is you're squashing everything from minus infinity to plus infinity on each side all the way in. And that's why you've got this strange shape here. If you notice here, the height of this cone only comes up to 0.2 in terms of the density, whereas you're up to 10 or more for the tails of this copula function. And if you look at the copula distribution function, again, you've got something running from 0 to 1 in terms of your inputs rather than plus and minus infinity, but your output, your result, goes from 0 to 1. It's a probability. So if you mapped instead where f of x and f of y were on these lines, plotted them up, you draw to the back and across, that tells you your cumulative probability, your probability that f of x and f of y are less than the amounts in which you're interested. Now, for the normal copula, it might be easier to run through an example, just to see exactly how we do it. So let's assume that you have got two data sets, say they're returns on a couple of assets, and you know they're linked by normal copula with a correlation coefficient of 0.7. And you've got two assets, each with a t distribution for their returns. Now, asset X has a mean expected return of 0.4, a scale of 0.15 and 8 degrees of freedom. Asset Y, mean of 0.07, scale of 0.17 and 5 degrees of freedom. So these are parameters for the t distribution. The scale is a bit like the standard deviation. So if you had an infinite number of degrees of freedom, the scale and the standard deviation would be the same. As the degrees of freedom come down, they start to diverge because the scale and the standard deviation, you get between them using the degrees of freedom of the t distribution. So the scale is what you'd use, but it's not exactly the same as the standard deviation of the observations if you calculated them. Now, say you wanted to calculate the probability that both assets produced a loss. So the return on both assets was less than 0. How do you go about that when you've got two marginal distributions which are both t-based with different degrees of freedom, and you've got a normal copula joining them both? So step one, you calculate the probabilities that x and y, so you calculate f of x and f of y, and you calculate that they are both less than 0. So what you're calculating is f of 0 for both x and y. Then what you do is you convert these probabilities into standard normal variables. So you take phi to the minus 1 of f0 for both x and y. Now what this step here is doing, or these two steps rather, is taking something which has a t-distribution and it's essentially just squashing it down so it's got a normal distribution, because you're swapping it from being t-variates to being a distribution function to being normal variates. And then when you've got these two numbers here, which are both standard normal variates, so if you plotted all of your results here, they'd lie in a standard normal distribution, they have a standard normal distribution. You use those as inputs into a standard bivariate normal distribution. So you calculate phi of rho, which is the correlation coefficient, of each of these two things here. Phi to the minus 1, f of x naught, phi to the minus 1, f of y naught. Now this looks very messy. This was actually used, this equation was actually used on the cover of Time magazine just after the global financial crisis, because it was blamed for the global financial crisis because the bivariate, or actually the multivariate normal copula was used to price CDOs and other similar exotic fixed income derivatives, and it was the mispricing of these which caused contributed to the global financial crisis. So believe it or not, this has actually featured on the cover of one of the world's most popular magazines, but not many people would know how to use it. But by the end of this talk, hopefully you will. So let's look at step 1 again. Step 1, f of 0 for x and y. The probability that x is less than 0, that's actually 0.3982, and the probability that y is less than 0 is 0.3488. So how do we do this? Now this is going back to some fairly basic statistics. If you want to know the probability that some observation with a particular distribution is less than a particular amount, what you need to do is first calculate the equivalent amounts assuming it had a standard distribution. So these have got a t-distribution, and we've got a mean of, for asset x, you've got a mean of 0.04, scale of 0.15, and 8 degrees of freedom. So if you want to know what the probability that it's going to be less than 0 is, the first thing to do is shift it so that your distribution has a mean of 0. And that means taking 0.04 of both things. In other words, you want to know what the probability of an observation being less than minus 0.04 is if the mean was 0. But then you want to say, well, what if it had a standard scale, a scale of 1? And the way to do that is you divide the result by 0.15. So you get 0 minus 0.4 divided by 0.15, that is a standard t-variate. So instead of looking at the probability that your returns are less than 0 with those parameters, you're now looking at the probability that some observation is less than minus 0.2667, but this has a mean of 0 and a scale of 1. And if you put minus 0.2667 into a standard t-distribution with 8 degrees of freedom, you get out a probability of 0.3982. So that is your probability for x. You can do the same thing for y with a mean of 0.07 and 0.17 scale and 5 degrees of freedom. You just knock off 0.7, so you centralise your distribution, divide the result by 0.17, so it turns into something which has a scale of 1, and that gives you a standard t-variate of minus 0.4118. And if you plug that into your t-distribution here, you end up with a probability of 0.3488. Okay, so now we have two probabilities, 0.3982 and 0.3488, two f of x's, or rather an f of x and f of y. So what do we do with these? Well, we turn them into standard normal variates. So we take 5 to the minus 1 of f of x naught of this probability here, and we get minus 0.2579. And take 5 to the minus 1 of f of naught for y, which is this here, we get minus 0.3886. Now, the interesting thing here is, look at this one here for x, minus 0.2579. If you look at what the standard t-variate was, it's minus 0.2667. So you can see it's fairly close. And if you look at y, it's minus 0.4118. Here it's minus 0.3886. So they're actually fairly close, and that's because all you've done is squash the distributions a bit. You've made them a little less fat-tailed. You've pushed your observations a bit more to the centre. You've started with something which has a t distribution. You've then changed that such that it has a standard t distribution, and then you've flipped it to a probability and then back so it has a standard normal distribution. And that is essentially just taking a distribution and squashing it a bit. So we have these two numbers here which are standard normal variates. And because we've got standard normal variates, two standard normal variates, what you can do is you can plug these into a bivariate normal distribution. So this horrible looking formula here, all it really means is you take 5.7 of these two normal variates, minus 0.2579 and minus 0.3886. And what that gives you is 0.2522. 0.2522 is the probability that both x and y both give you returns of less than 0. So that's all there is to it for using a normal copula. And hopefully that puts a bit of meat on the idea of how these things work, that you take your marginal distributions, whatever they are, you squash and squeeze them into a standard distribution that you want, which fits with your copula, for a normal copula anyway, and then use that as an input into a fairly standard distribution. So again, just to recap once more, if you think about the x variable, it had a t distribution with a mean of 0.4 and, where are we now? Mean of 0.04, a scale of 0.15 and 8 degrees of freedom. So what we first do is we shift the distribution so it's over 0, we scale it so it's got a standard scale, we change it from being a t distribution to a probability, we change that probability back into a normal distribution. Because if it's a normal variate, you can just use the bivariate normal distribution. And you could have done that whether it was t distributed, gamma, log normal, anything. It doesn't matter. So that's how you use a Gaussian copula. So, just to reiterate again, those that prefer to see it in words rather than hear it, take t distributed data, stretch each of the two items so they've got standard normal distributions, then treat the results as a standard bivariate normal distribution. And the same principle is true for any of these similar copulas, things like a t copula or a Gaussian copula, normal copula, anything where you're essentially using a bivariate or multivariate distribution to define the copula. What you do is you stretch and squeeze your univariate observations such that they look like the thing that you'd use in a standard bivariate or multivariate distribution. Now, this stretching and squeezing, it does raise a bit of an issue around correlation. So I just want to take a short while to look at how we think about correlation in the world of copulas. We did have the correlation in the previous example, and it was Dow's rho, and Pearson's rho is what it's generally known as, which is whenever anybody talks about correlation, they usually mean Pearson's rho, the product moment correlation coefficient. Now, it is the standard correlation coefficient, but it isn't necessarily going to be the same between two sets of data if you squeeze and shape those distributions. Importantly, if you're using Pearson's row for distributions which do have quite strange shapes, then that shape will influence what your answer is, even if the order of observations between the two marginal distributions is unchanged. And we can see this through an example. So just to finish on this point, so for normal copula, for example, it's possible to compromise and use row based on stretched data. But a better alternative is to use a different measure altogether and to use a rank correlation coefficient. Because a rank correlation coefficient is calculated using the order of the observations. So the values of those observations don't matter. Now I'm not going to look at the formula for these here, but just look at some of the properties of them. So the two most important ones are Spearman's rank correlation coefficient and Spearman's row, Spearman's rank correlation coefficient, and Kendall's tau. They're also very important for a particular type of copula, which we'll talk about once we've finished on correlations. But here is an example. What I've got here are two normally distributed data sets. And Pearson's row between these is 0.74. Spearman's rank correlation coefficient, calculated using the order of data, is 0.709. And Kendall's tau is 0.511. Now, if you look here, we've got observations going from, a scale going from -30 to +40. And, you can and these lines indicate how the observations are linked. So the time period where you had your lowest observation for series X was the time that you had your second lowest observation for series Y. And it was reversed for the second lowest observation of X happened when you had your lowest observation of Y. So these lines here can be thought of as being time markers. So it doesn't matter what order they came in terms of which was first and which was last, but when this observation was seen for Y, it happened at the same time that this observation was seen for X. Now, let's look and see what happens if we change the distribution for Y. So what I've done here is I've changed it to a very fat-tailed distribution. It's so fat-tailed you can see the scale here went from -30 to +40, now it's going from -80 to 100. And the observations for X, these are unchanged. The observations for Y, they're changed, but the order is still the same. So you can see that your lowest observation for X happened at the same time as your second lowest for Y, and that's reversed again. Your second lowest for X is when you had your lowest for Y, and so on. So all these lines, they're still joining things in the same order. So although the distribution for Y has changed, the relative order in which the observations occur is exactly the same. But you can see if you do this, Pearson's row changes. It goes down to 0.7. That's because when you're calculating Pearson's row, you're looking at the standard deviation as well as just the order of the observations. The value of these observations is taken into account when you're calculating your correlation coefficient, not just where they are. But Spearman's row and Kendall's tau remain unchanged. We can also stretch them in a slightly different way. So instead of having something which goes from -80% to +100%, you could have something which goes from 0 to 100% or 0 to 1, but still keeping the order the same. Lowest here, second lowest above. Second lowest here, lowest above. And the other time linkages are the same. So what kind of distribution could you have where you have something running from 0 to 1? Well, a distribution function. So if you calculate the distribution function for each of your marginal distributions, this bit here, these lines, they're essentially the copula. They're the bit which say what the time dependency in this example of these different series is. And that's why using a rank correlation coefficient is better suited to copulas, because the rank correlation coefficient, it actually fits very well with this approach. In fact, if you calculate Pearson's row, the standard correlation coefficient, based on the order of the observations, based on the distribution functions of these observations, you find that Pearson's rho is actually exactly the same as Spearman's rank correlation coefficient, even though the calculation is completely different for the two. And you can see here, Spearman's rho 0.709, Kendall's tau 0.511, as they have been in each of the previous examples. So a lot of the time when we're using copulars, the best thing to look at, the best approach is for correlation is one of the rank correlation coefficients, either Spearman's rho or Kendall's tau, partly depending on the copula that you're going to use. Now this is particularly important when you're looking at Archimedean copulars, which are a very particular, a very simple type of copula that you can use. The interesting thing about Archimedean copulars, one of the interesting things about Archimedean copulars is that it works directly on a copular distribution function. So what do I mean by that? If you think about something like the normal distribution, as you'll recall, normal distribution, the density function is reasonably easy to evaluate. It's a fairly straightforward formula that you can use to calculate the value of the normal density function at any point. If you want to calculate the distribution function at any point, it is actually rather difficult. You need to you actually essentially need to manually calculate what the volume, what the area under that chart is at each point, because the density function has got an e to the x squared in it, and you cannot mathematically integrate e to the x squared. So you need to work it out the long way using computing power or a really large sheet of squared paper or something similar. Archimedean copulars, of course, that means if that's what you need to do for the distribution function, it's also what you need to do for a Gaussian copula, a normal copula. It'd be exactly the same approach. You can't work it out mathematically, or you can't work it out just by integration. You need to work it out by calculating computationally what the volume underneath that copula would be. So Archimedean copulars are a bit easier. What you do with an Archimedean copula is you calculate the distribution directly. So the output is the joint density function, the joint probability density function, or the joint probability distribution function, or the copular distribution function. That is the answer that you get out without having to worry about using numerical methods to calculate what the answer is. So, as we've seen from the previous slides, the inputs to a bivariate copula are f of x, f of y, and for a multivariate copula you just extend it. So you go from f of x1, f of x2 all the way to f of xn. And each of these can take a value from 0 to 1. Archimedean copulars give you an easy way to combine f of x1, f of x2 up to f of xn into a joint probability. So you can do this with Gaussian copulars, but Archimedean copulars are so much easier, honestly. What you do is, and the way to think about this is in terms of the ranges of what these different things can take. Because you've got all these individual distribution functions that lie between 0 and 1, and you want to kind of aggregate them somehow into some joint distribution function. And the way you do this is using what's called a generator function, which is denoted psi. So the generator function is something which takes each of f of x1, f of x2, f of xn, and turns it from a number between 0 and 1 to a number that lies between 0 and infinity. Now, this is good because then all you need to do is you take each of these generated numbers and you add them all together. And when you add them all together, the result is also something which lies between 0 and infinity. And what that means is this generator function that you've taken, that's converted f of x1, say, to a generated value, you just use the inverse of that generator, because that will take any number between 0 and infinity and convert it to a number between 0 and 1, which is the joint probability. So here is a pictorial representation of how this works, of what it means. So you've got a whole load of observations here, or a whole load of distribution functions for these individual variables. So you might have had a t-distribution or whatever in the start, but you've taken f of x1 and you've got a distribution function for this observation and a distribution function here. So this is the probability that some random variable capital X1 is less than or equal to x1. This is the probability that some random variable capital X2 is less than or equal to f of x2, and so on all the way down to f of xn. And all of these, because they're probabilities, they all lie between 0 and 1. But when you apply this generator, what you end up with is psi f of x1, a number which lies between 0 and infinity. And that's true for all of these generated numbers. So if all of these lie between 0 and infinity, just add them up together. The sum of them will also lie between 0 and infinity. And because this generator is really good at turning things that go from 0 to 1 into things that go from 0 to infinity, it means that the inverse of the generator is really good at turning things that go from 0 to infinity from 0 to 1. In other words, it turns it from this number here to a joint probability. So that sounds fine in theory, but how do you control what the relationship between these variables is? Well, here's an example. This is an Archimedean copula called the Gumbel copula. It's got a generator function of minus log of f of x to the alpha. So if you apply that formula to each of the f of x, sum them, and apply the inverse generator function to the total, you get a cumulative distribution function. You get a copula function, a copula distribution function. And this number alpha, that's what determines the relationship between them in terms of what the strength of the relationship is. And what is alpha? Well, you can define alpha as being 1 over 1 minus tau. What's tau? Tau is Kendall's tau, a measure of rank correlation. So in other words, if you've got a couple of data sets, you calculate the rank correlation coefficient between them, Kendall's tau. That can tell you what parameter you should use if you wanted to link them using a Gumbel copula, which is really neat and actually pretty straightforward compared to some of the other approaches. Now these are three of the most popular Archimedean copula distribution functions. You've got the Gumbel, which here has an alpha of 4, Frank has an alpha of 14, and Clayton an alpha of 6. The relationship between the parameters in these copulas and rank correlation coefficients isn't necessarily straightforward. Sometimes it's Kendall's tau, sometimes it's the Spearman's rho, but it is still a different approach and a more direct approach than using a copula which is defined by a multivariate or bivariate distribution. Now, one thing which you might notice from these three charts here for these copula distribution functions, which, as I say, these are the things which are actually directly generated by Archimedean copulas. What you might notice is they all look almost identical. And even if you look at these contour maps of the distribution functions, they all look pretty similar. And to be honest, that's the main reason that we even look at copula density functions, because this doesn't really give you any indication of what the relationship really looks like. If instead though you move to the copula density functions, so essentially you differentiate the distribution function, or you look at the slope of the distribution function at different points, you get these density functions. And what is interesting here, I mean, if we look at the Clayton one, that's probably the most interesting one. You can see that it rises much more here than it does here. What that means is that if you were thinking in terms of, say, returns on a portfolio, and your biggest fear was the risk of things all going wrong together, so you think they're jointly fat-tailed, well, that's what this represents. On the downside, you've got jointly fat-tailed. On the upside, you haven't. So this is useful mainly for giving an indication, allowing you to visualise what the relative shapes of the distributions is. And one of the key things about these Archimedean copulars is potentially the difference in the shapes of the copulars at the tails, the extent to which you've got what's called lower or upper tail dependence. How fat the tails are in the copula, how jointly fat the tails are in the copula, either at the lower end or the upper end. So that's most of what I wanted to talk about today, really. The only other thing I wanted to spend a little bit of time on was just how you choose a copula. Because there's all these wonderful approaches here, but how do you actually decide which copula you should use? Parameterising the copula is relatively easy. When you're parameterising a copula, all you really need to do is, once you've decided what copula you're going to use, is you calculate the appropriate correlation measure using the appropriate data, and you use that to work out what the parameter of the copula is. But choosing the actual copula to use is potentially more difficult. What you can do is you can do standard goodness of fit tests, things like chi-squared tests, where you essentially look at your data and then you look at what the data will be on the, if it is from the copula, you look at the difference between them, which gives you the best fit. But you can also think about what the appropriate shape should be. Do you have jointly fat tails on your distribution? Then a T-copula is going to be more appropriate. Do you have different levels of tail dependence, upper and lower tail dependence? Then an Archimedean copula could be appropriate. But it's worth mentioning here one of the limitations around Archimedean copulars that you might have noticed is you've got to choose a single measure of correlation. So looking across all the data sets that you've got, you decide on average the correlation is whatever, 0.6, and then you calculate your parameter appropriately. If you've got a complex correlation structure, so you have different correlations between different pairs of variables, then you might want to use a normal or a T-copula, which is going to reflect this level of complexity. But make sure you need this level of complexity. And one of the things in the financial crisis where the Gaussian copula was used, a Gaussian copula was used, but the same correlation coefficient was assumed for all pairs of observations in many cases. So what this meant was that you had something which had the ability to give an awful lot of granularity around the relationships, and it just wasn't used. So it could be that it would have been better to just use an Archimedean copula, particularly one which had lower tail dependence, and a single correlation through the whole lot. One thing to be aware of here is the fact that when you're looking at joint tails of a distribution, by definition they have relatively few observations. If you've got two data sets, the bottom left tail is essentially that set of observations where things have gone wrong for both, say, Series X and Series Y. So you might have a particular probability that the observations of Series X will be below a particular level. And you might have a particular probability that the observations of Series Y are below a particular level. But the probability that they're both below a particular level is going to be, by definition, even lower at a particular level. So you need to recognise that the probability that both below a particular level is going to be, by definition, the more asset classes you add. So you need to recognise that the probability that both below a particular level is going to be, by definition, the more asset classes you add. So you need to recognise that the probability that both below is what is going to be, by definition, the more asset classes you add. So you need to recognise